Hi everyone. In this lesson, we tackle short rate models, restricting ourselves mostly to one factor of short rate models, though I'll also say a few words about multi-factor models right at the end. We'll derive an analog of the Black-Scholes PDE, the so-called term structure PDE, and list a number of short rate models from the literature. In particular, we discuss the class of so-called affine term structure models, which have a very nice mathematical structure and are very tractable in some detail, and we'll investigate various instances of these affine term structure models, such as the Vasicek model or the Cox-Ingersoll-Ross model. We'll also have a look at the pricing of interest rate options. So let's start. This particular video is concerned with the derivation of the aforementioned term structure PDE. Short rate models are bond market models or term structure models where the only explanatory variable is the short rate R, i.e. the instantaneous forward rate right now. This is the earliest mathematical approach to bond market models, dating back to the Vasicek model in 1977. Recall that the Black-Scholes model was published in 1973. Short rate models appear to have very limited power, because they use only one value, namely the value of the short rate, to model the entire yield curve, which consists of instruments going out to 30 years or more. Nevertheless, principal component analysis shows that typically 80 to 90% of price variation in the bond market can be explained by a single factor. I'm not going to explain how principal component analysis works here, but it is useful to get some notion of how it works. I've therefore uploaded a separate short set of lecture slides on principal component analysis and the yield curve. In particular, it has been observed in many data sets that three principal components explain almost all the variation in the yield curve, and that moreover, these three can often be interpreted as controlling the level, slope, and curvature of the yield curve. Let's consider one-factor diffusion short rate models under the real-world measure P. And let's assume that the short rate dynamics are given by an Ito process as follows, where mu and sigma may be stochastic processes themselves, and W is a one-dimensional Brownian motion under the objective measure P. Typically, mu and sigma depend on both T and R, in which case we have a so-called Ito diffusion. In this setup, the only primitive security is the riskless bank account. Remember here that riskless means that there is no credit risk. As the short rate is a stochastic process, there certainly is interest rate risk. All other term structure instruments can therefore be regarded as derivatives of the short rate. We assume that there is a risk-neutral measure Q, such that all discounted bond prices are Q martingales. In other words, such that the following equation holds. In particular, this implies that the price of a zero coupon bond is simply the conditional risk-neutral expectation of this exponential. Further recall that if the Radon-Nikodym derivative of the risk-neutral measure with respect to the objective measure is given by this Dolian's exponential, then by Kirsanov's theorem, the risk-neutral dynamics of the short rate are given as follows. In other words, we subtract the volatility times the Kirsanov kernel from the drift, but leave the volatility of the short rate unchanged. Let's now start with the derivation of the term structure PDE. Recall that by the Markov property of Ito diffusions, the price of a T-bond at time little t is given by a function f. In other words, the price of the T-bond is given by a function f, which is a function of time, the short rate, as well as the maturity. Here the maturity is really a parameter rather than a variable, as it doesn't change for the underlying bond. And thus we will also write this function as follows. We assume that each of these functions f superscript t is sufficiently smooth and differentiable to allow the application of Ito's formula. Now, to derive the term structure PDE, we will mimic the naive derivation of the Black-Scholes PDE. In other words, we will create a locally riskless portfolio but using two bonds of different maturities, S and T. By arbitrage considerations, the drift of this portfolio must be equal to the short rate. And as for the Black-Scholes model, this results in a partial differential equation. If we apply the Ito formula to the function f superscript t, we obtain the following expression, where here the subscripts denote partial derivatives. So for example, this is the second partial derivative with respect to r, this is the first partial derivative with respect to t, etc. Now we will divide this expression by f superscript t. In other words, we will divide it here, and here, and here, which leads us to obtain the following expression. Here, alpha superscript t is given as follows. And sigma superscript t is given as follows. Now, consider a portfolio V consisting of S and T bonds with relative weights Ws and Wt respectively. Here the weights add up to 1. You can then show that we obtain the following stochastic differential equation. dV over V is equal to Ws times dFs over Fs. Here F superscript S is the price of the S bond, plus Wt dF superscript T over F superscript T. That is easily seen to simplify to the following expression. Now we'd like to make this portfolio locally riskless. In other words, we would like to remove the Brownian component. And thus, in order to eliminate the risk, we must set this expression here equal to 0. Since the weights also add up to 1, we have two equations in two unknowns. The unknowns are Ws and Wt. And this can easily be solved as follows, as you should verify yourself. When we take these expressions for the weights and plug them into here, we obtain the following equation. Namely this equation here. As this is locally riskless, there is no Brownian motion component, by no arbitrage the return on V must be the riskless rate, and therefore this expression here is equal to the short rate. A little manipulation shows that you can rearrange this expression to put all the S terms together and all the T terms together. Thus this expression here, alpha minus r over sigma, is independent of the maturity of the bond. It is the same for the S bond and for the T bond, and S and T were arbitrary maturities. Therefore, it depends only on T and the short rate and not on the maturity of the bond. Notice further that alpha T is the drift of the T bond and sigma T is the volatility of the T bond, and therefore this expression here is just the drift minus the riskless rate over the volatility, which is precisely the market price of risk. It therefore follows that any two zero-coupon bonds have the same market price of risk, lambda. This lambda may depend on T and RT, but it does not depend on the maturity. It follows that in an arbitrage-free one-factor short-rate model, given by the following dynamics, there is a process, lambda, which is a function of T and the short rate, so that alpha T minus r over sigma T is equal to lambda for all maturities, where lambda is just the market price of risk. We can now show that all bonds satisfy the following term structure PDE. Notice that this is a second order backward PDE in terms of time and the short rate R, and that it contains the market price of risk. The terminal condition here simply states that the price of a T bond at time capital T is equal to 1. Now, in order to show this, we start from here using the expressions for alpha t and sigma t that we derived before, namely alpha t is equal to this and sigma t is equal to this. And if we stick these values of alpha t and sigma t into this expression over here, we obtain the following, which can then be easily rearranged to yield the term structure PDE as shown above.